Okay, so looking at this class, we still have some people that have not turned in the first week. Well, let's see. We have two people that have turned in the first week, but I don't see them in class either. And that may be why they're one of them is not in class. Two people still not turned in our very first assignment from a couple of weeks ago. We have one, two, three, four, five people have not turned in last week's assignment, and one, two, three, four, five, seven people have not turned in the quiz from last week. So, getting behind already. It's only January 21st, and some of you are starting to get way behind already. So, this is the beginning of our usual normal virtual schedule. So, we have class today. And then Thursday is not required for everybody. Every class up till this point this semester has been required for everybody. By the way, this is an A-Day Friday. So this class will meet again on Thursday. But the only people that's required to be here are the people whose grade is below 70%, which is basically the people I was talking about, right? If you haven't turned in the last 2 weeks' assignments, or haven't turned in the quiz. Let me see. Everyone just yep. Everyone that's not turned in the quiz, your grade's below 70%. Because the grade is worth 30 of the 70 points we've had so far. And if you haven't turned in, that's a 0 for you. So right now, those 7 people that's not turned in the quiz, your grade is below 70%. And there are some of the people that have done the quiz that did not do well on the quiz, grades below that. Now, I don't know if I set the quiz to allow you to take that more than once. A lot of times I do, so you might check. If you didn't do well in the quiz, go look at what you missed, review the quiz, go back and look at the assignments of those questions you missed to say, what did I do wrong? Especially if you did better on the assignments than you did on the quiz. What did you do differently on the quiz? What did you mess up? If you need to review the class video, if you need to come to class Thursday and say, Mr. Brock, I took the quiz, but I didn't do well. Can we review that together? Absolutely. We'll go over the quiz together if we need to. But if you have not turned in the quiz, your grade is below 70%, and you will be required to come to class on Thursday, but not Friday, because Friday's an 8-day. So don't get any further behind, guys. Don't get any farther behind. Some of you are starting to drop back already, and that's not good. You don't want to start the semester this way because you'll end up the whole semester behind, and that just gets to be a real headache and it's stressful when you are behind on all of your work all semester. So get caught up. Take the time. That's all I can say. That's all I can say. Now, the folks that have got things turned in, you're doing pretty well. I'm looking at like last week's assignment, not the quiz, but the assignment. Wow, a lot of 100% and some 80%. A lot of 80 and 100% on that. Only one person did less than an 80% on that, and they still passed it. I mean, it's all right. So you guys are understanding the log functions pretty well, because a lot of times we struggle with log functions. You did pretty well. The exponential functions, a lot of 70s, 80s, 90s, and 100% on that. So a lot of that's going pretty well for a lot of you. And even the quiz, I'm seeing a lot of 87%, 100%, 84%. Several people did really well on that. So that's not too bad. 77%, a few 100s even. So I'm liking how that's going for those of you that are doing it. But I'm really worried about the ones that are already behind and we're not score yet. So, all right, let's take a look at what we have this week. All this fun stuff. Thank you for having your cameras on, by the way. Most all of you have your cameras on, and I appreciate that a lot. There it is. Let's go to our grade screen as usual, the place that I recommend you always start when you log into Buzz to see what have you turned in, what did you score, when was it due, what's due this week. So everything you've turned in, you should have a grade for already. Should show what date you turned it in and how you scored. and have the due dates over on the side. So this week, the 26th is this Sunday. So we're doing the graphing, 2 assignments about graphing exponential, graphing log functions. So we do those together. That's we're going to use Desmos on that. So we can do both of those lessons during class today without worrying about it. I'm sure we can do that. These we broke up into 2 different ones, but we'll do both of these. 505, 506. But yes, if you're behind, go to the grade screen. It'll tell you what you have not turned in. And you can go back and redo that if you didn't do well. 5.05 right here, graphing exponential functions lesson. We're going to start there. Then we'll look at that assignment and then look at the graphing logarithm functions. Oh, this is the Sierpinski lesson. I remember this. Wacław Sierpinski. What a name, huh? Wacław. We don't name anyone Wacław around here, but he was a Polish mathematician over 100 years ago, back during World War I. He worked with fractals. And you're like, fractals? Yeah, fractals is a branch of mathematics. You can go to college and study fractals, and I don't know, good luck finding a job, but still, it's one of those things. Fractals. That gave us the Sierpinski triangle here. If I share this correctly, we can hear the proper pronunciation in case I'm saying it wrong, because you gotta say it correctly here. All right, here's a little right here. You can hit and hear the correct pronunciation of his name.
Sierpinski. Sierpinski.
Sierpinski. Got a little bit of a flair to it. Sierpinski. So that is Wacław Sierpinski. So a fractal, what is a fractal? It's a geometric figure that you divide into pieces, which are very similar in shape to the original, but smaller. So squares inside squares inside squares could be a fractal. This is the Sierpinski triangle. Like I said, it was about 100 years ago when Sierpinski put this together, and we're going to relate it to exponential functions. It's kind of interesting. So let me pull this video up here, and let's spend 1 minute and 8 seconds checking out the Sierpinski triangle.
One method of creating the triangle is by first drawing an equilateral triangle. Remove another, smaller equilateral triangle from inside the original. The vertices of the removed triangle meet at the midpoints of each segment of the larger triangle.
Okay, let me pause that for a second to make sure you caught that. The way you remove this triangle is you find the midpoint, so the exact middle of each side, and that's going to be the point of the new triangle. The exact middle of each side, so that this triangle that was removed is exactly the same size and shape as the 3 blue ones that remain. And all of them are miniatures of the original triangle. So you're removing a triangle from the exact midpoints.
Next, 3 more equilateral triangles are removed from inside each of the remaining 3 triangles. The process of removing triangles inscribed within the larger triangle can continue forever.
So that's the Sierpinski triangle. And like it says, that can continue forever, but it's going to get really, really small and hard to see. But you just continue removing triangles taken from the midpoints of the remaining triangles. And you're like, okay, what does it have to do with our graphing exponentials? Well, you'll see coming up here. So for this lesson, why does the average rate of change vary on an exponential function? What effects does adding a constant have? In other words, transformations. And how can exponential functions be utilized to fit existing data? So Sierpinski's triangle actually demonstrates an application of an exponential function. Remember, an exponential function is the variable located in the exponent. And the base of the function has to be a positive real number that's not 1, because if it's 1, it's just a constant line at 1. So example, f of x equals 3 to the x power. So that's what Sierpinski's triangle is. An exponential function is a function of the variables located in the exponent, and its base is not equal to 1. The exponential function being used in Sierpinski's triangle is f of x equals 3 to the x power, where x is the stage at which triangles are removed, and f of x represents the number of triangles remaining. So after the first stage, 3 to the first power is 3. The first stage, you take out that one triangle in the middle, and it leaves 3 blue triangles. So that's why this is an exponential function. The second stage, you remove triangles from each of those, and it leaves 3 squared, which is 9 triangles after the second one. So we got a video that's going to kind of take a look at this.
The exponential function is f of x equals 3 to the x. At stage 0, when x equals 0, the function equals 1, indicating there is only one solid triangle. This is how the fractal begins. At stage 1, f of x has a value of 3. This means that the first time a triangle is removed from the center, there are 3 triangles left. At the second stage, f of x has a value of 9. So 9 triangles remain. At stage 3, f of x has a value of 27. So the third time equilateral triangles are removed, 27 triangles are left, and so on.
And so on. So yeah, it is a representation of 3 to the x exponential function there. So that's kind of cool. So the next time when they remove 3 more, now there'll be 81 little bitty triangles, and so on and so forth. Sierpinski's triangle. So it says, let's graph the exponential function demonstrated in Sierpinski's triangle. Okay. All right, so if we graph this, this is the graph of 3 to the x. Graph of 3 to the x. So we see when they're at the beginning, before any triangles are moved, we have one large triangle. And then when you get up to where the first stage of Sierpinski's triangle, it moves it. Now there's 3 triangles left. And then the second stage, there's 9 triangles left, and so on and so forth. And quickly becomes a very large amount of triangles as it goes up. By the 5th triangle, by the 5th stage, we've got 243 triangles. It's the 5th time we do that. Where's it at? There it is. By the 5th stage, we have 243 triangles. So it's going to increase really quickly as Sierpinski's triangle comes along there. So there they put their little graph of the same thing. So when you look at that, it says the domain, which is all the x's, is all real numbers, right? This will go forever. This direction, it goes forever to negative infinity. And this will keep going to infinity, but it's going to go up even faster. But it'll eventually make it all the way down here. It's just going to be up in the millions or bigger by the time it gets there. But that is the domain. Now, what is the range of this? Well, when we look at it, we see this goes to infinity for the y's, but how far down does it go? I don't see any negative y's. I don't see any negative y's at all. It looks like it comes down here and just sits on 0, but it doesn't. It actually, if we zoom in, see right now it says it's 0, but if we zoom in, let's see how far we can zoom in here. It still thinks yep, it still thinks it's 0. Well, let's keep going in then. If it keeps thinking 0, still think it's 0. Yep, still thinks it's 0.
You have to go up and click the little highlight.
Oh, now it's not 0 anymore. We've zoomed in enough to where it's now, see that 1.03924 times 10 to the negative 91? That's scientific notation. That means it's actually 0.00091 zeros and then 1.03924. So that's how small of a number it is. It's 0.91 zeros and then that 1.03924. So it's a very, very small number. This never actually, get back out there. It actually never does touch the 0. It looks like it, but it is actually, 0 is an asymptote. 0 is an asymptote. It'll never touch the 0. So the range is y is greater than 0. Even when it's 0.0000091 times 0.1, it still does not equal 0. And so that is the range of our formula. So the domain is all real numbers, but what's the range? Well, when x is -5, it's 1/243. When it's -4, it's 1/81, -3. See, as the numbers get more negative, the bottom of our denominator gets larger. 1/3, 1/9, 1/27, 1/81, 1/243. But it'll never equal 0 because there's always a 1 on top. So the range is y is greater than 0. So it has what we call an asymptote. Asymptote is a very cool word in the fact that, oh, here, let me emphasize this because it's the only one I'm aware of. Asymptote is the only word that is unique to mathematics. All the other words that we use, you can use them in other subjects too, and there's other meanings that mean, that can be useful. But asymptote is truly just a math word. It only means something in math class. Interesting. Just find one of those little trivial tidbits like that. Kind of cool. It's a unique math word only. So I put that back up there. We define an asymptote as an imaginary line that the graph of a function approaches more and more closely, but graphs will never cross a vertical asymptote. They could cross a horizontal asymptote or oblique asymptote. It's possible that they could cross them over, but it's a line that the function approaches more and more closely, the more it goes. So, all right, so let's look at some more exponential functions. We'll answer any of these questions below. So imaginary lines that a function or equation approaches are called asymptotes, and since the y coordinates of this function approach 0, there's a horizontal asymptote. All right, so this wants us to look at exponential functions. When the base, let's look when the base is greater than 1. Okay, so we can actually put that here in Desmos and look at it this way. If we have b to the x power. Now, when b is 1, this is just a horizontal line, right? Where y equals 1. 1 to any power is just 1. But if it gets bigger, okay, b is 2. This is 2 to the x power. This is what the graph looks like. Notice it crosses down here at x equals 1. I mean, y equals 1. When x is 0, y is 1. And it goes up like this. If we make it larger, now b equals 5. So this is 5 raised to the power of x. Still crosses at 0, 1, because any number taken to the power of 0 equals 1. Any number. So this is always going to cross here at 1. But notice how much more steep it is. And as I raise the number, it gets steeper and steeper and steeper. Got it all the way up to 10 now. We can make that even bigger if we want to go to 20. Let's go from 1 to 20. How about that? Steeper and steeper and steeper, all the way up to 20. Right. So the larger that number is, the steeper it is. So that's what they're illustrating here. If we have a number that is larger than 1, the larger that number is, the steeper it gets. Now let's look at a base that's between 0 and 1. Okay, so we're going to change this to be 0, and the largest would be, let's say, 0.999. Between 0 and 1. Look at this. The closer it gets to 0, well, 0, it doesn't exist there. See, there's 0.02. 0.02 raised to the power of x is really, really steep the other direction. It's coming down really fast as the x gets larger. But the closer this gets to 1, look how less steep this is. Less steep. The closer it gets to 1, the more flat this exponential graph. But notice, when it's between 0 and 1, it comes down. When this is larger than 1, it goes up. So base between 0 and 1. See over here. So if we put a 0.5 and a 2, these are reflections of each other. Actually, 0.5, 2. We do, let's see, 0.4 and 2.5. Kind of hard to see it with the way they have the y-axis there. So move the slider in point B with the basis of the exponential function greater than 1. Describe the graph. Greater than 1. So it gets steeper and steeper the larger the base number is. So steeper and steeper. Steeper and steeper. So this says, reading the graph from left to the right, as the x increases, the y also increases. And as the base of the function increases, the slope of the graph becomes steeper. So there you go. Domain's all real numbers. There's no horizontal aspect, but y equals 0. So the range is y is greater than 0. Next, uncheck the box greater than 1 and do the between 0 and 1. Describe the graph of an exponential function, the basis between 0 and 1. Okay, they're talking about the purple one here. Closer it gets to 1, the flatter it gets. The closer it gets to 0, the steeper it is. So it says as the x coordinates increase between 0 and 1, the y coordinates decrease, gets less steep. As the base of the function increases, the closer it gets to 1, the slope becomes flatter, less steep, and still has the same domain and range. What happens to the graph when the base is 0? Okay, let's take it all the way down to 0. Look there. 0 to the power of 0, it must be 0. 0 to the power of 1, 0 to the power of 2, it's all 0, but it doesn't exist from the negative end. The graph does not exist when x is a negative number. The graph is a ray on the x-axis from the origin going right. Starts at the origin, goes right. 0 raised to any positive exponent results in 0, since 0 times anything is 0. And when it's a negative, you got to remember our rules about a negative exponent. It's a positive exponent if you write 1 over that same number, and 0 in the denominator does not exist. That's why the graph does not exist. What about when the base is 1? It's just a line, because 1 raised to any power, 1 to the 10th, 1 squared, 1 to the 5th, 1 to the 138th, just equals 1. So that's why exponential functions can't have a base of 1, because it's not exponential anymore. It's linear. It's a line. All right, page 2. That was a lot on page 1, wasn't it? All right, we have another video. And we're going to look how to use one of these exponential functions that we studied like 2 weeks ago, but we'll take another look at another video here.
Today I'm going to show you how to use the properties of exponents to interpret exponential functions. In this particular set of examples, I'm going to be referring to the value of boats. I have boat 1, 2, and 3. So beginning with boat 1, the very first number you're going to see is 5,000. This is the initial value of the boat. The next thing you're going to notice is being multiplied by 1.25. This is our percent of change. What is happening to that initial value? And then our exponent of x is where we would put our numbers of years. So if I wanted to know how much his boat would be worth in 10 years, I replace this x with 10 and then evaluate this. So what else can I tell about boat 1? Well, we know, like we said, the initial value was 5,000, but it's being multiplied by 1.25. What does that tell us in terms of percentage? The number is greater than 1, so it is keeping its value, but it is gaining 25% in value. So if I were to classify this, I would say that it is increasing. So boat number 1 actually is increasing its value year after year by 25%. Now looking at boat 2, same thing. Notice we have the initial value first. It is a value of $4,000. Here our percent is 0.40, our percent of change, and we have the X for our number of years. Now the difference between these two, you'll see, is that this one is greater than 1 and boat 2 is less than 1. So what does that mean? It means that we're going to keep 40% of our initial value. So we know our percentages go up to 100. So if I keep 40, that's also saying that I lost 60. So if I'm classifying this one, I would say it's decreasing. I'm actually losing 60% of the value because I'm keeping 40%. So
I want you to stop and think about this too. Think about what the graph would look like, because this is actually what we did 2 weeks ago when we talked about exponential functions. So he's working some exponential functions like we did 2 weeks ago. But this week we're really focused on the graph. So think about it. That one would have 5,000 as a y-intercept. That's the starting value. And it would be increasing, with the second boat would have a 4,000. And we expect that one to be an exponentially going down as we graph that.
when I'm looking at boat 3, I have it just in words, but not in the expression. So how can we make that happen? Here we have an initial value of 4,500. The same as we have with boats 1 and 2 at our initial value. Then we're multiplying by our percent of change. So here it says it's losing 50% each year. So if we are losing 50%, that means we are keeping 50%, expressed as 0.50. And then the last thing we add is our x, which is our number of years. So we can easily determine by the way it is written here, our percent of change is less than 1, so we know it's decreasing. And of course, our problem actually says it loses. So we would say it is decreasing. Now, when you look at these two, we have 4,000 times 0.40 and 4,500 times 0.50. A lot of times we tend to think, oh, well, this is decreasing by a lot less because it is 0.40. But really, notice we are keeping 40%, meaning that we are losing 60%, as opposed to here, we are losing 50%. So if you were comparing these two boats, this one is losing value at a much faster rate than boat number 3. So knowing what these numbers mean and knowing how to classify them as increasing and decreasing be very helpful in interpreting these functions. And that is how you use the properties of exponents to interpret exponential functions.
Okay, so with that, when we look at Desmos, and we will have some notes on this, Beck, I was just thinking about that. Let's look at the Desmos graph of a couple of those right there, knowing that's increasing and one's decreasing. So if we go over to Desmos, kill this right here, take that off. Let's look at the first one. Y equals 5,000 and at 1.25 to the x. So he said this is increasing in value because this is greater than 1. And we were just looking at graphs. When the base is greater than 1, it does go up. And we're going to zoom out a long ways because this starts at 5,000 and we're down here at 15. So let's. Whew. So there, if we come in at 5,000, that's actually where it's going to cross the y-axis. Negative, negative, negative. We'll get to 0. There it is, 0, 5,000. 0, 5,000 is where it's, and it goes up exponentially from there. So if it's going up 25%, by the time it gets to 1, it's going to be much larger than 5,000. It's going to be 6,250 or whatever. So it goes up very, very quickly. But when we look at the other boats they had, like another one was y equals 4,000. And this one was decreasing. We only kept 40%, 0.4 to the x. And notice this one, when it crosses at 4,000, it's actually going down because, well, let me zoom out it back here. See, this one, the purple one's coming down. Well, it's not going to equal 0, but it's saying after 11 years, it's not worth a whole lot anymore, but it's losing 60% of its value every year. So it's coming down. So exponential, when the base is greater than 1, is going up. When it's less than 1, it's going down, which we can see that with the illustrations he's talking about. If your boat's only worth 40% of what it was worth last year, and you graph that, it's going down. So we can kind of understand how that works. It would be going down. So key features, that's what we talk about when we're graphing things. What are the key features of a graph? The y-intercept, that's always a key feature. So that's when the x value is equal to 0. All right, so let me put some notes on that. Let's talk about key features. Y-intercept. When we have like that f of x equals 5,000 and it was going at 1.25 to the x. We're like, well, the y-intercept is when the x equals 0. So what is this going to equal then? Well, it's 1.25 to the 0. Look it over here. 1.25 raised to the power of 0. What is 1.25 raised to the power of 0? What is 2 raised to the power of 0? What is 2,146 raised to the power of 0? What's 1,921,400 raised to the power of 0? What is Mr. Brock? I'm doing this to be silly. Mr. Brock raised to the power of 0. All of these answers are the same. Anything raised to the power of 0 equals 1. Anything. 1.25 to the power of 0. So when this is 0, this is 5,000 times 1. So that means at the very beginning, when no time has passed, it's still worth the original amount because 1.25 to the 0 power is 1. So don't forget that. At the y-intercept, it's going to equal whatever this starting amount is, regardless of what number is in here as the rate. Doesn't matter what that number is. At 0, it's going to be whatever this is, because anything to the 0 power. And if you need to test that, let's see. Let's put in 1,921,400 raised to the power of 0, and it equals 1. So anything to the power of 0 equals 1. So that's the y-intercept when the x value is 0, and since they're exponential functions, any base taken to the 0 power is equal to 1. And then we look at the end behavior. Is it going up to infinity, or is it going down to a specified value, the asymptote? So we're going to use, for this discussion, see, it says a to the x equals b to the x plus k. Okay, so we're going to get a little bit into transformations here. So here's the formula they're starting out with. Okay. A of x equals p. P is the starting amount, the starting principal, or whatever you're going to say, the starting value, what you start with. B is the base of our exponent. And then plus k, this is just a transformation. So let's see what it says here. If p is positive. Okay, so if P is positive. Whatever amount we're starting with. We've got some kind of value, 5,000 or 8 or whatever the number is. If the base is greater than 1, then our graph is going to look like this. And it's going to have an asymptote at K. Asymptote at Y equals K. Because whatever K is going to raise that asymptote or lower that asymptote, whatever it is, if the base is larger than 1. If it is less than 1, then it's going to be one of these functions, again, with an asymptote at Y equals K. Okay, so this is just a generic way to know what the graph is going to look like. And then we'll have P is negative. So down here, P is negative. Okay, so if P is negative and the base is larger than 1, or the base is less than 1. So we look at our little cheat sheet there. If it's less than 1, we'll say we have this Y equals K line again. It's going to go down like this. If the P is a negative, if there's a negative number out front, if this is negative 5,000, it's going to flip it upside down. And over here, and let's just for variety make Y equals K up here. Just, it doesn't matter what the K is. Y equals K. This is going to go up this way. I don't have that curve exactly right. But anyway. So generically, exponential graphs are either going to go up like this, down like this, or they could be upside down where they're going towards negative infinity or from negative infinity. But either way, they'll have that asymptote wherever Y equals K is. If there is no K, then K equals 0, right? The ones we were graphing on Desmos did not have a K, so they all had an asymptote at Y equals 0, but we could move that very, very simply. So there's a good little table for your notes. This one here, so you know that applies to those below. When P is positive or P is negative. So P is greater than 1, P is less than 1. And the K is the K. And note that it applies to this formula up here. All right. And that's right here on this page as well. So if you're copying that, didn't get all that. Page 2 has this, what is positive, negative. And we look at this. Let's take off this really crazy huge number. Let's just make it 5 and 4. All right. So it's down here as a reasonable numbers. But this, see, the asymptotes are at Y equals 0. If we put a plus K on there, we'll put this at a plus 4. Oh, sorry. Now the asymptote's at 4. Look, it's getting closer and closer. See, that's this line here. 4. Now that's the asymptote, 4. If we do this one at the other group one at -2, let's make our K a -2. Look, that is now the asymptote. It's getting closer and closer to -2. So that K at the end is equal to the asymptote. Y equals K. Nice little cheater there. So describe the y-intercept and end behavior of the following graph. We have a y-intercept of -1. The left end of the graph goes towards infinity. The right end approaches the asymptote of y equals -2. Check your work. The y-intercept 0, 1. The graph starts up on the left. decays downward and gets close to y equals -2. So up on the left, approaches the asymptote of y equals -2. The average rate of change. Okay, the average rate of change is just the slope, right? So like if we had 9x, that's linear. If Juan makes $9 an hour, however many hours he works times 9. Let's change this. So y equals 9x. That's linear. If he works 1 hour, he gets $9. He works 2 hours, he gets $18. He works 3 hours, he gets 27. The rate of change or the slope is the 9. But what about an exponential function? Let's say 9 to the x. What is the rate of change? The rate of change is constantly changing. It's constantly changing because right here the slope is very, very small. But as we get here, now the slope gets steeper and steeper and steeper. So the average rate of change can only be found between 2 points. But anywhere on the graph, we can't tell what the rate of change is. What is the rate of change right there? I don't know. It's different. That's calculus. Calculus, you'll actually get in the calculus class, you will figure out what those rates of change are. But in this case, we say, what is the rate of change between 0 and 1? Let's say that. I'm going to change this graph to where it does all the ones, but doesn't put the minor ones in there. Okay. Well, let's change this to like a 3, something more reasonable. So let's say, what is the rate of change between when x is 0, all right, and when it's 2? Oh, not x, 2. See, those 2 points are on the graph. I can ask average rate of change between those 2 points because that is a constant number. As far as the rate of change anywhere along here, that's very, very, very different because it's getting steeper and steeper and steeper. But between these 2 points, the slope is 4. Look, y equals 4x plus 1. See, it goes through both those points. So yeah, the rate of change between when x is 0 and x is 2 is 4 because it goes up 4 over 1, up 4 over 1. That is the slope between those 2 points. So remember, anytime it asks for you average rate of change, it's simply asking for the slope. So you would just draw a straight line from those 2 points and figure out what the slope is. And the slope is 4 between those 2 points. So let's see. Oh, here's like a skier going down a mountain, right? It starts up at this height, ends up down at this height. Now, at different points, sometimes the mountain was pretty steep. Other times it was not very steep. But overall, there's an average we can take to say on average it was this steep all the way. If it was perfectly straight, that would be the average rate of change. But at different points, it was different amounts of steepness. If we look at how someone drove, they started at 0 hours, and 2.5 hours later, they were in Gainesville, which means in 2.5 hours, they drove 140 miles. They averaged 56 miles an hour. That was the average rate of change. That's drawing a straight line from where they started to where they finished. But if we look at their actual trip, in the first hour, they made 70 miles. They drove 70 miles an hour. And then in the next hour, they didn't make it very far. They made it like 15 miles, 18 miles. They probably stopped for lunch or gas or something. And then again, they were driving 70 miles an hour. So at no point were they actually driving 56 miles an hour. But if we look at the start to the end and make a straight line, their average was 56. Okay, let's put that in there. Tell me where you got it. And there's the same thing right there. Average 56. All right, find the average rate of change. Oh, let's do this problem together, because you'll have some problems like this. Okay, I've got this written down. This is what they want us to find. The average rate of change with this equation between x equals 1 and x equals 3. Well, the easiest way to do that is like, okay, what is f of 1? 3 times 4 to the first power, because x would be 1. 4 to the first power is just 4, so it equal to 12. It's 12 when x equals 1. When x equals 3, 3 times 4 to the third. Let's get our calculator to make sure we get this right. 4 to the third power is 64, because that's 4 times 4 times 4 times 3. That's 192. So it's 192 when it's 3. It's 12 when it's 1. It's 192 when it's 3. So 12 minus 192 is 180 negative. 1 minus 3 is negative 2. So negative 180 divided by negative 2, average rate of change of 90. Because it's 12 when it's 1, it's negative 192. It's 192 when it's 3. If we subtract those, 12 minus 192, 3 minus. You could also do it the other way. You could do 192 when it's 3 minus 12 when it's 1. This would be a positive 180 divided by a positive 2, and it's still 90. So it doesn't matter which way you do it, you'll get the same answer of 90. But just put what they equal, subtract it, subtract what X has got those values, and find the average rate of change of 90. So first you have to find what those values equal. 1 equals 12, 3 equals 192. And then we subtract them. The slope formula, y2 minus y1 divided by x2 minus x1, and you get a slope of 90. So that's good to have in your notes. A nice example problem there on how we found the average rate of change between 2 points using the equation right there. And either way, you don't need to do both of these. Either way, but you're subtracting one from the other. Page 3. We got to get moving. We're taking up a lot of time with this lesson. Worst case scenario, we push it back. So up until this point, we've only worked with the general form. So let's talk about transformations. That's the next thing we need to discuss. Transformations. And this we will definitely put in our notes as well. Transformations. So how does transformations affect? If we have f of x equal some starting amount, our base raised to a x minus h plus k. You know, we usually use h and k as our transformation letters, right? This is a b, whatever the base is. What happens when there's an h? What happens when there's a k? So let's look in Desmos first to see what happens so we can generalize some kind of notes for that. So we're going to give it a number. We're going to say right now that our principal is 2, our starting amount, and it's going to, let's just make it 1. Let's make it real simple. And it doubles, and we're going to do x minus 0. We're going to make h0 right now. And our k is going to be 0. So this is h and k at 0, right? We can see that. It's just a 1 out front. It's doubling x minus 0, k is 0. So we're going to copy that, make a second one. What happens if we change h to be 1? Or 2? Or 3? Every point moved 1 to the right. This was 0, 1. This is 1, 1. This is 2, 4. If I can get on it. 2, 4. This is 3, 4. It didn't want to go in here. I'll do it this way. 2, 4. And 3, 4. See those points? Those points are on those graphs. Everything moved 1 to the right when you subtract 1. So if h is greater than 0, so it's x minus h is 1. Graph shifts right by h. Right? If h is 1, so it's x minus 1, the graph to shift right by 1. If h is 3, it'll shift right by 3. So then if h is less than 0, let's say h is a negative number, what do we expect? This is exactly the same that's happened with every other transformation. It's going to go left by h. And we're going to look at that too. So if it's negative 1, negative 1. So I put negative 1 in there to where we can see it's less than 1. And now it's over here. It's at 1, 4. It shifted left. Everything shifted left. The point that was 0, 1 is now negative 1, 1. Everything shifted left because this is a negative. Now, generally, if this is a negative, though, you won't see x minus negative 1, right? You'll see x plus 1. You'll see x plus 1. But that is x minus negative 1. But that's what you would see if I gave you a problem. It wouldn't say x minus negative 1. It'd say x plus 1 because that's the same thing. That's the same thing. All right, so now let's look at changing k. All right, we're going to go back to x minus 0. So we're back on our original spot. But we're going to change k to be plus 2. Look what happened now. Every single point went up 2. So I'll put that on our notes. If k is greater than 0, there's a number out here that's a plus 2, then it's going to shift up 2. K is less than 0. Why am I putting graft? Oh, man, my brain is not working. I knew this morning I felt off. Graph. Graft. So if k is less than 0, the graph's going to shift down by k. We can see that on Desmos as well. If we change this to a negative 2, now the graph went down 2. Now we're at 2, 2 instead of at 2, 6. Every point went down 2. The y-intercept went down 2. 1, 2 went down to 1, 0. Everything shifted down 2. So transformations work exactly the same. So this you can play with. You can play with up and down with the K, left and right with the H, just like we were looking at. So, all right.
Like it should.
So this wants us to look at graphing, exponential graphs, 1/3 to the x. Oh, this is a good example to show because to graph this correctly, you may need to use parentheses. Equals 1/3 raised to the x. That's between 0 and 1, so it's a graph that goes downward. F of x equals 3 to the x. But those are reflections of each other, 1/3 and 3. They're reflections of one another. This graph is a reflection of the y-axis of 3 to the x, which we just saw in Desmos. Here is 2 to the x plus 1. All right, so if we graph f of x equals 2 raised to the power of x plus 1, we're going to put that in parentheses so it keeps it all together. Let's turn those off. See, that's a transformation of 2 to the x. But everything shifted 1 to the left because of that negative 1. 1 to the left. Been shifted over. 2 to the x plus 1. That's going to go up 1. That's a k, right? So we see that everything shifts up one. We were just looking at that on the other screen. And then the last one is, they showed X left and right, K up and down, just like we have in our notes. All right, let's look at page 4, see what else they're going to throw at us here. Oh, fitting functions to data. Okay, so finding best fit. Okay, so this is something interesting. Sometimes we've got data and we don't know what the function is. And so this is going to have us play with this to figure out what is best. So we got these 5 points. 5 points, right? -5, -1. So let's move these points, A, B, C, and D, E, to those points. -5, -1. So where's -5, -1? That is right there. A is now on -5, -1. Then our next point is -2, -1. -2, -1 right there. Then we've got the point 0, -2 right there. 1, -3. I missed it. Right there. And the last point is 2, -5. 2, -5. Now we see that kind of looks like an exponential graph, but can we come up with an equation to make that match? So let's change our base to we're gonna make our coefficient negative. All right, so it's a negative coefficient because that's what our chart showed us in the first time. If we want it to be a reflection down, we need a negative coefficient. See, it's -1, no, -2. Our base, if we make our base larger, it's going to be steeper. We don't need it that steep. Let's go down to negative. Oh, no, that's 2. Let's shift it to the right. What do you say? Oh, that'd be a -1. Let's shift it down, -1. Oh, that's pretty close. That's pretty close. We've got everything but the B. But we go right through A, went right through C, went right through D. This is a kind of interesting thing. You can play with this on page 4 on your buzz lesson. Find some coefficient values. And I found 2 different ones when I've done this in the past. So this would be -2 times 2 to the x minus 1 minus 1. So we're translating it 1 to the right. No, to the left because it's -1. So it'd be x plus 1 up there. And K be -1. So we brought it down as well. That's it. So what they come up with? 2, 2, -1, -1. They found the same thing. But you can play with that and come up with a formula that fits it the best. Now, it doesn't fit it exactly because our B is off, but this is a line of best fit. It's the closest you can get to most of the points. Because if we change these numbers, now we're way off. Say we can get to the B. If we play with that enough. Oh, A and B right there, but we don't hit C, D, and E. So we got to get close as we can. Oh, let's see there if I raise it up 1. No, that doesn't work. Stick with our numbers we had. Right there. Let's look at page 5. A miniature course just for you. So you just won a miniature golf course thanks to a contest you entered. But you're going to learn that running that's not as easy as making sure the windmill's turned on. You have to set the prices based on the market. The arcade needs maintenance. The concession stand needs to order food supplies. The list goes on and on. And each of these demands can be represented by a function that reflects the profit. So if you set the prices at $5, then 5 times X would be how much money you get, 5 times every person. So you want to develop a way to account for everything together so you can just change things and see it happens. So combining functions algebraically. So let's take a quick review if we had f of x and g of x. Right, f of x is 2x plus 8, right? And g of x is x plus 4. So we can add these functions together and come up with a function. We can subtract functions, come up with a function. We can multiply them, or we can divide them, right? That's the four things we can do with functions. We can add them, subtract them, multiply them, divide them. We could also insert one inside the other one, but we're not looking at that right now. But we can do that with these functions. So how does this affect exponential and log functions? So if we have 2 to the x and x plus 4, we can also do those things. We can add them to the x plus 4. We can subtract them. We can multiply them. We can divide them. 2x divided by x plus 4. So let's start analyzing this golf course. Now, we talked about the tickets to be 5x, $5 for every ticket. So more visitors mean more money, but also more trash. So the trash removal, we figured out would cost us 50 cents times a race of 1.1 to the x. So every person that comes in is going to cost us 50 cents, and more trash exponentially, 1.1 to the x. So if we can combine these, how do you think that would combine? Subtract, because this is profit, 5x. This is cost for picking up trash. So we'd subtract them. So we could say 5x minus 50 cents times 1.1 to the x. And so if we had 40 visitors, let's take a look. 40 visitors, 5 times 40 would make $200, but it would cost us, the 1.1 to the 40th power is 45.26 times 50 cents. It would cost us $22.63. We'd end up with a profit of $177.37. If we had 70 visitors, now we're taking this to the power of 70, and that equals $789.75 times 50, which means, look, we brought $350 in, but we spent $394.87 picking up trash. We actually lost $44.87. So we don't want 70 visitors. Maybe charge more, we'll have less people come in. 40 visitors, nice profit. 70 costs us too much. And here is a graph. If we look at the graph of this function, we can see we make the most money at about 45 visitors. Oh, maybe close to 50 visitors. This is 40 and 60. But about 50 visitors. But after that, we start quickly losing money because there's so much trash to pick up. It costs us more to pick up the trash than what we make on profit. You can also look at this. A recent boom in birthday parties has multiplied the cost of trash that's removal to 2x. So now if it's 2x, the cost of trash removed by the function g of x equals 2x. So the function gx is multiplying the cost, so we combine it with the r of x to get x times 1.11 to the x, because 2 times 1/2 is now just $1. If there's 16 visitors, it's going to cost $73 to have the trash removed. This is just the removal. This does not combine the sales. This is just the cost. And you see it exponentially goes up very, very fast. Let's look at our lesson summary. Here's the 3 questions we started with. An exponential function is a function where the variable is located in the exponent and the base is limited to positive real numbers not equal to 1. When you use a graphing software like Desmos, set up the code, enter 3 to the x, or if it's x plus 1 or whatever you got to put in parentheses, your graph should look like this, with a range of y is greater than 0 and a horizontal axis of y equals 0, unless you have a k. Key features: y-intercept, in behavior, average rate of change. And a function is said to be the best fit if it passes through the most data points. And functions can be done by either adding, subtracting, multiplying. And you can divide, as we looked at earlier too. So let's look at the lesson that goes with this first one, just to see if there's anything we haven't covered. Which graph models this function? Well, that's pretty easy to figure out, right? Because you can say, I'm gonna copy that, but when I paste it, it's not gonna look right because you got to fix the exponent. So that's this, but the x should be an exponent. Okay, so that's what the graph of -4 times 2 to the x is. Which one of these is that? Looks like it's that one. Yep, that looks like it. Giving the parent function 2 to the x, which shows when we add a 1 on the end, k becomes 1. What happens? Does it go up? Does it flip upside down? Does it go down? Or does it go up to about 1.5 when k equals 1? Again, that's not too bad. Let's see. The boat's value is given as the function 400b to the x, but which graph shows the boat decreasing 25% per year, which means we remain 75%. So it'd be 400 times 0.75 to the x. You got to zoom way out, right? Because 400 is way up here. But it's losing 25%, so it keeps 75%. So which one of these graphs shows that? Both of these start at 400, but where is it like at 3? Is it way down here about 50, or is it up here about 160? That's what you got to tell when you look over here. It's at 3, and we're zoomed way out right now. So 3, is it about 50, or is it a lot higher? Okay. Describe the y-intercept and end behavior. Well, y-intercept should be able to look right there. So we can rule 2 of them out right away. So the graph either approaches -6 to the right, or the graph decreases to the left. No, to the left, as it goes right, it's decreasing. And the last one here is a representation of tickets from a theme park. Theme part, I love it. Theme part, 3x, and the cost to pay the employees is 1.25 to the x. So here's the function of those combined. So after 5 seasons, estimate the profit. Can you read a graph? Number of seasons. At 5, what's the profit? Is it 2, 5, 12, or 18? Okay, don't make that harder. That's pretty simple. Let's look at the next lesson real quick, see if we can get it covered in the 20 minutes we have left of class. I think we can, because it should be a lot shorter. It is 1 through 4. So what do you remember about graphs and their reflections? Remember, we saw this before. If we reflect this over an imaginary y-axis, then that would just reflect to be this, right? She was facing to the right. Now she's facing to the left, because the y-axis is the up and down axis. That's right. It just reflects it over the y-axis. And they had these that we looked at these before, an imaginary y-axis again. Well, it'd be the same way up. It just switched positions where the popcorn's on the right side. And then they had over the x-axis, this would reflect down. So this guy over here would still be on the right side, but be upside down. This guy over here would still be on the left side. So that would be this one. This, they're upside down, but they've changed places. So that's not just a straight downward reflection. Correct. And then our last one was x-axis. So the dog would still be facing with his head to the left. It would just be right there, straight down. Correct. So graphs of logarithms are basically a reflection of the corresponding exponential. So the line y equals x is the line that it reflects over. So it talks about y equals 10 to the x. Let's go down here. Being a reflection of f of x equals log x. And they reflect over the line y equals x. Right? We can see that it reflects perfectly over the line. So everything over here is exactly the same distance as everything over here from that y equals x line. So that's what they're showing us here, is that it's a perfect reflection if you have the same corresponding logarithm of the exponent. You remember we can rewrite logarithms to exponents and exponents to logarithms. And if you rewrite it and graph both of them, they will be reflections. Characteristics of the graph of the common logarithm right here. Domain. In exponential, it's all real numbers, right? Because it goes from negative infinity to infinity. But in the logarithm function, x is greater than 0. Because look, there's an asymptote at x equals 0. See, the logarithm over here does not go into the negatives. It doesn't even hit 0. It just gets close. For the exponent, it's the y that doesn't hit 0. So those change places. X is greater than 0. Over here, it's y is equal to 0. And this is all real numbers. The range for a log is all real numbers. These just trade places. The asymptote is the x-axis on an exponential, but the y-axis on a log. So this is the review on that. Page 2. Let's take a look at some additional examples of graphing log functions. X minus 3. Let's look at how it works. Get rid of everything else. If we put in parentheses and say minus 3. Oh, I got to put it after the x. Minus 3. Look, it shifted to the right. I'm going to put the original equation up here. Y equals log x. See, everything moved exactly 3 to the right. Because this is like the h. So let's write that in our notes right there. Let's do this. Same. Works the same. X minus h. If h is 3, it's going to shift right by 3. If it's x minus negative 3, or x plus 3, it's going to shift left by 3. It's the same. Just like it was the same for quadratics, it was the same for third degree functions, it's the same for linear functions. When h is greater than 0, it shifts right. When it's less than 0, if k is a positive number, it goes up. If k is a negative number, it goes down. Same. We just need to know where the h and the k is. H is there, the k is there. With the logarithm, it's right there. Let's do an x plus 3 or x minus negative 3. All right, x minus negative 3. Look, it shifted left. But we would normally see that as plus 3, right? X plus 3 shifts left. Let's do the plus k plus 5. Oh, let's do plus 3 so we can see it on our screen. Everything shifted up 3. That's minus 3. It all shifts down 3. It works exactly the same. Exactly the same as what we've seen with quadratics, the same as what we saw with exponents, logarithms, exactly the same. So that's great. We don't have to have different rules. We can see it does exactly what we thought it would do. Shift to the right when h is 3. So x minus 3. And you may notice the y-intercepts get really close to the y-axis, but they do not have a y-intercept. Do not have a y-intercept. The only way to get a y-intercept, let's see. The only way to get a y-intercept is with a transformation, right? If we put plus 1, now it's got a y-intercept. Now it's got a y-intercept. Lesson summary. So a logarithmic function is the inverse of an exponential function. And you can see that in its reflection. And shifting works exactly the same. Plus 6 is a horizontal shift, goes to the left. Outside the x is a vertical shift. All right, I want to look at the assignment here, but I'm just now deciding because this is, I didn't put a template in there. I think I'm actually going to cancel this assignment because I don't know that it's that critical that we need to know how to do this. But the assignment is actually found at the end of the lesson on page 4. where you have to graph f of x equals negative log 10 of x. Figure out where it's 0, where it's 1. Raise this. I tell you, I'm going to cancel this assignment. We've looked at this. You understand exponents. This is a reflection of it. Yeah, I'm going to cancel that. So I'm going to go in and excuse that for everybody. Just because I don't know that that's really critical that we do over that. So I'm going to do that. I will give you a break there because I want to. And I don't think we actually just have to have that exactly. But anyway, we finished with 10 minutes to go. Hey, Truce, hang around. Let me get you the login so you can get into Buzz. But everybody else, this is an A-Day Friday. This is an A-Day Friday. So we will only meet on Thursday, and you only have to come if your grade's below 70%, right? We're starting our regular schedule this week. So tomorrow, your A-Day class is a meet since yesterday was a holiday, but we only meet Thursday morning. So if your grade's below 70%, I'll see you Thursday. Or if you're struggling to do this assignment, you can come to class even if your grade's 100. I'll be here, and I'll be happy to help you if you're stuck on anything. But otherwise, we're basically done for the week. We've gone through our 2 lessons. You've got your 1 assignment, and we'll see you Thursday or next Tuesday, whichever applies for you.